Light pipe. Light enters a solid pipe made of plastic having an index of refraction of 1.6. The light travels parallel to the upper part of the pipe. So you can see it travels parallel to the upper part of the pipe. You want to cut the face AB so that all the light will reflect back into the pipe after it strikes that face. So it strikes this face and then it reflects back into the pipe. Part A, what is the largest that beta can be if the pipe is in air? So beta is the angle between the AB cut and the path of the light, incoming light beam. And part B, if the pipe is immersed in water of index 1.33, so if we take this pipe and put it into water, what is the largest that beta can be? So what is the meaning of asking this light beam to be reflected and get basically stay all the way into the pipe, so it reflects back into the pipe, and that means there's no refraction, so none of the light energy will be transmitted into the air or the water in part B. So basically we want no refraction. And how is this possible? That means we're asking for total internal reflection. All right. So let's start with part A. So here is the light beam coming parallel to the top of the plastic pipe, and it makes an angle beta with this cut, AB cut. Therefore, it makes an angle 90 minus beta with respect to the normal to this surface, and the plastic has an index of refraction n. So for total internal reflection, we're going to have n times sine 90 minus beta, the angle it makes with the normal, greater than or equal to 1, the index of refraction in air, times sine 90. So the condition for total internal reflection is that if you have no refraction, the angle of refraction should be 90 degrees or more, so that we will have light staying completely inside. We're taking the index of refraction of air to be approximately equal to 1. So the sine of 90 minus beta is cosine of beta. So cosine of beta should be greater or equal to 1 over the index of refraction of the plastic material. Now, given that this angle beta will be a value between 0 degrees and 90 degrees, cosine of the angle, cosine 0 is 1, cosine 90 is 0, is basically between 1 and 0. So cosine beta decreases from 1 to 0. So as beta increases from 0 to 90 degrees, so we can say that cosine beta decreases as beta increases. All right. So we find that cosine beta should be greater or equal to 1 over n, implies that beta should be less or equal to cosine inverse of 1 over n. So that's the condition on beta here. It should be less or equal to cosine inverse 1 over n. So if I substitute n here, beta is less or equal to cosine inverse 1 over the index of refraction of the plastic 1.6. So I find that it should be less or equal to 51.3 degrees. So beta should be less or equal to 51.3 degrees. So let's try having a beta value greater than beta max. If beta is greater than beta max, let's take, for example, beta to be 60 degrees. Okay, if I write Snell's law and sine 90 minus beta is basically 1.6 sine 30, it would be 0.8, which would be 1 times sine theta for refraction. And I would find that sine theta is 0.8, which means there will be refraction. So I conclude that beta cannot be greater than 51.3 degrees. Now in part B, we're changing the medium outside. For the total internal reflection condition, we have the index of refraction of the plastic 1.6 sine 90 minus beta should be greater or equal to the index of refraction of water 1.33 sine 90. All right, so that's in part B. We have a refractive index 1.33 for water, what is the largest that beta can be. And once again, this is a cosine beta, and this gives me beta is less or equal to cosine inverse 1.33 over 1.60, which is 33.8 degrees. So the maximum value that beta can have is 33.8 degrees. Okay, so we have light entering a solid pipe made of plastic, index of refraction 1.6. It travels parallel to the upper part, and then it stays inside the plastic. We are considering two cases. The outside is air or outside is water. We want to know the largest possible value of beta. For the total internal reflection, so for total internal reflection, TIR, we have n times sine 90 minus beta, so that's the angle this light beam makes with respect to the normal to the surface, AB surface, is greater or equal to 1 sine 90, so that's index of refraction of air is 1. And that gives us cosine beta is greater or equal to 1 over n. Since as beta increases, cosine beta decreases between 0 and 90 degrees, beta is less or equal to cosine inverse 1 over n, which is 51.3 degrees. Indeed, if I try to have a value of beta greater than this, 60 degrees for example, I see that sine theta for the angle of refraction is sine inverse of 0.8, which is possible, so there will be a refraction. If the outside medium is water, then we change this condition. 1 sine 90 becomes 1.33 sine 90. And in this case, beta is less or equal to cosine inverse 1.33 index of refraction of water divided by 1.6 index of refraction of the plastic, which gives us a maximum beta value of 33.8 degrees.